Hello, my name is Ileana Jelescu, and I'll be giving a lecture in this Tractometry course about modeling white matter. I would like to thank the organizers for the opportunity to teach today. I will start off by explaining diffusion MRI basics, and then we'll move on to introducing the diffusion tensor imaging and how we can use it to characterize white matter microstructure. And finally, I will spend time on biophysical models of white matter and how they can bring more specific information about microstructure. So let's start with diffusion MRI basics. Diffusion MRI gives us access to the mesoscale. What do we mean by that? So in an unrestricted homogeneous medium, such as this glass of water, the displacement probability function of the water molecules diffusing is governed by a Gaussian distribution. Now in biological tissue, because the water molecules are actually not free to move around, but their path is actually largely influenced by the cell membranes they encounter and other forms of restriction and hindrance, this displacement probability is no longer Gaussian. This becomes then similar to this drunk person trying to make their way home, and where their path is actually affected by the lampposts or building walls that they may actually hit while walking. And the MRI voxel size is on the order of a few millimeters, but the typical length scale for the microstructure in the white matter that we're trying to characterize is rather on the order of the micron. But serendipitously, actually, the mean displacement of the water molecules diffusing in this medium in the diffusion time that we impart in our sequence is actually on the same micron order as the typical microstructure features. So this is how diffusion MRI becomes actually an excellent probe of tissue microstructure. So how do we impart diffusion weighting in our MRI sequence? The most traditional scheme is called pulse gradient spin echo, or PGSE. And we start off with spins that are aligned or see a homogeneous field in space. And we apply a diffusion field gradient in one direction of space that creates a linearly varying total field. And therefore, also at the end of this gradient pulse, the water molecules have acquired a phase that depends on their position along the direction of the field. Then, because diffusion is happening, these water molecules mix. We apply a 180 RF refocusing pulse, and then we apply a second diffusion field gradient that is supposed to undo completely the effect of the first one. Now, because the water molecules have mixed in the meantime, actually the phase accrued in the second gradient pulse does not compensate fully the one accrued in the first gradient if the molecules have changed their initial position. And as a result, at the end, when we add up their contributions vectorially, they actually do not add up coherently, which results in our signal attenuation. So the signal attenuation that I mentioned due to diffusion will increase with diffusion weighting, so how much phase warp we impart here and how long we let the water molecules mix before we rephase them. But it will also increase with the actual diffusivity of the tissue. You can see this on these images here. For example, these are images with increasing diffusion weighting, and you can see that the signal is more and more attenuated as we increase the diffusion weighting in each voxel. On the other hand, within each image here, for example, you can see that the contrast is different. For example, the CSF has completely lost its signal with this B value because it diffuses very fast, while the white matter here still retains some signal because the diffusivity there is slower. Furthermore, in particular in white matter, the signal attenuation due to diffusion depends on the direction in which we applied this field gradient here. So within the same overall diffusion attenuation, the direction will change the image contrast completely. Here in the corpus callosum, we retain a lot of signal throughout, whereas with this direction, we only retain a signal in the central part, and with this other direction, actually the corpus callosum signal is heavily suppressed. Finally, how do we quantify the diffusion weighting that we've imparted? Essentially, we have three parameters. We have the amplitude of this gradient, its duration of this gradient pulse, little delta, and the separation of these two lobes between tagging and untagging the water molecules, large delta. And the so-called B value is actually a combination of all of these parameters that can be roughly separated into two major contributions. On the one hand, we have the Q value here, which is completely driven by the surface area of these gradients, and that relates to the phase warp that we impart in space, and the diffusion time T, which is the time that we let the water molecules mix before we refocus. And the phase warp has very distinct influence actually on the diffusion weighting. Here, this is an electron microscopy image of white matter where you can see axons cross-sectionally. If you imagine I apply a low Q value, it means that a field was slowly varying in space, and therefore inside of each axon, for example, the water molecules roughly see the same field, so they won't be dephased. However, if I apply very strong Q, actually within even the length scale of an axon diameter here, I start to have contrast because there will be phase loss due to mixing of these water molecules inside the axon. So the Q value and the diffusion time actually have a different impact on how we probe the microstructure. Now coming back to our displacement probability function, we actually now realize that the signal that we measure is a convolution between the density of water molecules that experience a certain displacement R, so this is related to the displacement probability, and the excess phase due to the displacement R that the water molecules accumulated, which is also related to the Q value that I apply in my sequence. And in the case of Gaussian diffusion, we actually know this displacement probability. It's a Gaussian, as the name would suggest. And therefore, the signal is none other than the Fourier transform of this Gaussian displacement probability. And the Fourier transform of a Gaussian is yet another Gaussian. So the signal is overall an exponential in minus q squared. And if we also convert this q squared t here as we re-express it as the b value, this is how the diffusion signal becomes a mono-exponential decay as a function of b value. Finally, if I look at the log of the signal, this of course now becomes a linear decay with b value, with the slope actually giving a measurement of the intrinsic diffusion coefficient of this free medium. Now in the case of biological tissue, of course, this probability is no longer Gaussian, as we've explained, and therefore we do not know how to invert this equation, or we do not know actually how the signal formally should behave. But what we can do actually is that we can, for example, measure the signal at various Q values, so try to sample Q space and perform the inverse Fourier transform of the signal in order to retrieve empirically this displacement probability function. This was sometimes used in order to retrieve an orientation distribution function of the fibers, which was highly beneficial for tractography, for example. Now, if we consider again the signal decay as a function of b value, in the Gaussian medium, of course, this is a linear decay of the log of the signal as a function of b value. And in the non-Gaussian or biological realistic case, since we don't know this function here, we cannot really characterize it, but we can measure it, right? So we measure this signal decay as a function of increasing b value. And what we realize is that there is a regime here in the low b value range where essentially still, even in this tissue, the decay of the signal can be approximated by a linear function, which reminds the Gaussian case. So in this low b value regime, we are in the so-called Gaussian approximation or DTI regime, where we can approximate the log of the signal to go roughly linearly with the b value, and this time the slope, so the initial slope of the decay here, we term as apparent diffusion coefficient because we are neglecting some higher order terms. Now let's go from the apparent diffusion coefficient to the diffusion tensor and see how we can relate that to white matter microstructure. As I have alluded to, the apparent diffusion coefficient depends on the direction in which I impart diffusion weighting. If I take again the example of white matter, if I impart diffusion weighting more or less perpendicularly to axons, the apparent diffusion coefficient, or ADC, that I will measure in this direction is relatively low because it's difficult for the water molecules to move when they encounter so many restrictions from the myelinated membranes. On the other hand, if I apply the diffusion direction more or less parallel to the axons, the ADC I will estimate will be much higher because of course it's easier for the water molecules to move along the axons. And so when we reconstruct the diffusion tensor, this matrix essentially allows us then to predict what the apparent diffusion coefficient will be in any arbitrary direction of space that I may not even have measured or sampled. I can project this tensor onto that direction and predict what the ADC will be in that orientation. And so this diffusion tensor is essentially a 3 by 3 matrix, which is symmetric. So there are only 6 coefficients to estimate. And mathematically, this matrix is invertible with all eigenvalues real and positive, which means I can find a basis where this tensor is diagonal, so all the off-diagonal elements are 0. And this is characterized then by 3 eigenvectors, and these 3 eigenvalues, lambda 1, lambda 2, lambda 3. In white matter, of course, you can see the principal eigenvector will be aligned along the axons, and the second and third will define the plane perpendicular to the white matter bundle, in the case, of course, of a single fiber in the voxel. In order to estimate the diffusion tensor, minimally, I need one B0 image, so non-diffusion weighted image, and 6 measurements that are diffusion weighted in non-collinear directions on a given shell or B value. So typically, to stay within the DTI approximation, we acquire data with B 1 millisecond per micrometer square, or in vendor or scanner units, 1,000 second per millimeter squared of B value. From this tensor, we can of course examine the eigenvectors, and in white matter in particular, the first eigenvector gives us the direction of faster diffusion in the voxel, so that's the one along the axon bundle. And this was extremely useful in the early days of tractography for tracking fiber orientations from voxel to voxel. We can also consider the 3 eigenvalues and then derive some scalars from it in order to come up with quantitative parametric maps. For example, we can calculate mean diffusivity, which is none other than the mean of the 3 eigenvalues. And remarkably in brain, actually, this MD contrast gives us little gray to white matter contrast. Roughly, mean diffusivity is pretty much 1 micrometer squared per millisecond everywhere in the brain. Now, if we calculate radial diffusivity as the average of the 2 lowest eigenvalues, this now gives us good gray to white matter contrast. And of course, radial diffusivity is lowest in white matter, again, because imagine it's harder to diffuse radially or perpendicular to the axons. We can also measure axial diffusivity in the form of the highest eigenvalue, and this gives us some gray to white matter contrast, and axial diffusivity is actually highest in white matter because there is this avenue here for water molecules to diffuse almost freely parallel to the axons. Finally, we can derive fractional anisotropy, which is a measure of the variance between the eigenvalues, and this can go from 0, that defines perfectly isotropic diffusion, so the ADC would be the same in any direction of space, to an FA of 1, which would define a fully anisotropic case, where diffusion, for example, would be unidimensional along a single direction, and the other directions having a 0 diffusivity. This FA, of course, gives us excellent gray to white matter contrast, and FA, as you know, is extremely high in white matter. Now, the DTI representation is extremely valuable, but it does have some limitation in that it lacks specificity. For example, if I measure an increase in radial diffusivity in a white matter voxel, what does it mean? This could be due to demyelination, axonal loss, or edema. Essentially, all of these processes will lead to the same effect on the MRI measure, and we cannot therefore inverse the mechanisms and determine what actually happened to the tissue just by measuring radial diffusivity. So this is why we at some point need to resort to using biophysical models of white matter, and in order to characterize the microstructure in a more specific and compartment-oriented way, we have to go beyond this DTI approximation regime and start looking at how the signal behaves in the higher B values, where it deviates precisely from a Gaussian, from the behavior of a Gaussian compartment. So this brings us to the final section of this lecture, which is about biophysical models of white matter and how we can characterize microstructure. So biophysical models of diffusion are about drawing the right picture. If you remember when I mentioned DTI, this is really a signal representation. I just described how the diffusion signal decayed as a function of B value, and I made absolutely no assumption about the underlying tissue. Now in biophysical models, this is the opposite. We have to draw a simplified sketch or schematic of what we think the tissue looks like and what are the relevant geometric features for water molecules to diffuse in this tissue. So this is now we start having, for example, biophysical models that are specific to white matter, some that are specific to gray matter, and of course the same for other tissues in the body. And then we have to go through a certain number of processes. The first one is which microstructure features are truly relevant for the tissue at stake. Essentially, what features do I retain in my simplified sketch here? Can I sensitize the diffusion MRI signal to those features? If I cannot, possibly they should not be a part of my model. And finally, can I reliably estimate all the model parameters from the data? So let's see how we fared with each of these steps when it came to white matter modeling. So what is a relevant model for white matter? Essentially, we consider multiple compartments and how the water behaves in each of those. First of all, it's fair to consider that in white matter we have a collection of axons, and then we have the water in this intra-axonal compartment that we model as a collection of either cylinders or in some simplified cases sticks, as I will explain a bit later. So in the cylinder case, we have the intra-axonal diffusivity and then the perpendicular diffusivity radially to the axon that then can give us some information on this axon diameter. If we assume that they are sticks, this diffusivity radially goes to 0 and the axon diameter is estimated at 0 as well. We just care about the intra-axonal diffusivity. This intra-axonal compartment is also characterized by a signal fraction f, which is also some measure of axonal density. And of course, some orientation distribution function. If we don't consider the axons are fully parallel, we can consider some dispersion among them. And all of these parameters are, for example, useful markers of axonal density or loss. In the case of the ODF, of alignment or pruning. In the case of the axon diameter of axon caliber, and the intra-axonal diffusivity is a very good marker for intra-axonal injury. Then we have water in the extra-axonal compartment that is usually modeled as an anisotropic connected space. So in axons, we have restricted diffusion. In the extra-axonal space, we have hindered diffusion because the space is connected, so there is no hard boundary. And this is characterized by two diffusivities, radially and parallelly to the axon bundle, and of course a water fraction, relative water fraction as well. The extra-axonal radial diffusivity is typically a very good marker for demyelination and the parallel one rather for inflammation. Finally, if one thinks it's useful, we can also consider a third compartment that will take on the cerebrospinal fluid contribution. So CSF can be modeled as a Gaussian isotropic compartment where the diffusivity is fixed to that of free water at that temperature. And then we can just estimate its relative signal fraction to the total signal. And the signal fraction can then be used as a marker of edema or atrophy. So there has been a very long effort in the community to try to estimate axon diameters from diffusion MRI measurements. And this has been going on roughly since 2008. Now, the initial DMRI estimates of axon diameters were up to 10 times the histology estimates, but gradually, actually, people have, in different groups, have come to understand where this immense bias was coming from. First of all, there is a confound from orientation, dispersion, and undulation that was singled out using oscillating gradients. And then the problem is that most of the time, people have been working in a low Q regime, where, as I have explained earlier, we have very little attenuation inside axons. So it's almost impossible to get contrast and estimate this intra-axonal radial diffusivity here, because although the water molecules mix, they don't dephase, because my field overall here on such a short scale was homogeneous. And so using the gradients that are typically present on clinical systems, so say for example up to 80 millitesla per meter, we can only characterize typical distances on the order of 4 to 8 microns, which is much larger than the white matter axons that are roughly 1 micron in diameter. And in this particular case, the diffusion time dependence is actually dominated by extra-axonal water rather than intra-axonal water, so any estimate that we get would rather be of the axon outer diameter. Now, with better gradients, we can start actually probing intra-axonal diameter, or the axon inner diameter as well. But for this, we need at least gradients on the order of the connectome, so 300 millitesla per meter, or larger in the case of animal scanners. And we can start probing characteristic sizes on the order of 1 to 5 microns. So this is very encouraging, and there has been really a lot of progress in this field. Now, in most cases, so if you just acquire diffusion data on your regular clinical scanner, say to characterize a clinical population, most likely you will be in some kind of long time limit and work with moderate Q value, in which case you have no sensitivity to axon diameters. So this intra-axonal compartment now is best modeled as a collection of sticks. So this diameter and diffusivity are set to 0, but everything else we keep, so the ODF and the intra-axonal diffusivity and so on. And this time also in this regime, the extra-axonal compartment can be modeled as a Gaussian anisotropic connected space, so there is no longer diffusion time dependence, but everything else is the same. So this so-called white matter standard model seems quite simple when we describe it, and it has a certain number of parameters. But if you look at the literature, there's actually a constellation of implementations of this same model. And the reason for this is that once we write the equations analytically and we try to estimate the parameters from the data, we realize it's a very difficult inverse problem to solve. And so in the literature, you may have encountered a certain number of acronyms such as NAUTI, spherical mean technique, or diffusion basis spectrum imaging, or again, white matter tract integrity. All of these are implementations of the standard model, but each of them makes different simplifying assumptions in order to stabilize the fit. For example, in some models, the axonal and extra-axonal parallel diffusivities are set equal to each other and to some fixed value. The tortuosity model is also largely used that relates the extra-axonal radial diffusivity fully to the intra-axonal water fraction and the extra-axonal parallel diffusivity. Or some models get rid of the orientation distribution function, assuming the axons to be perfectly parallel. Now, all of these assumptions have been proven to be actually invalid, and these first two are the assumptions underlying NAUTI or SMT. This one is the assumption underlying the WMTI. And the problem with these is that, imagine, for example, due to pathology, you have a genuine change in intra-axonal diffusivity because the cytoplasmic environment has changed. If this value is fixed, then that change has to be captured or absorbed by another parameter in the model that you've let free. But therefore, this introduces a huge loss of specificity for the remaining free parameters that absorb changes that are not directly related to themselves. Now, in the recent years, there has also been tremendous work towards moving away from spurious assumptions. And actually today, there are frameworks that introduce minimum assumptions and enable us to estimate the standard model fully in all of its parameters that I've introduced previously. And I gave here two examples. So one is WMTI Watson that can be directly derived from diffusion kurtosis parameters. Another one is standard model imaging that can derive parameters from rotational invariance, both of which have publicly available code. And finally, it's also encouraged to acquire richer data in the form of diffusion relaxometry or even diffusion tensor encoding, so moving away just from linear encoding along one direction to a sphere or a plane in order to remove some of these degeneracies and estimate all of these model parameters reliably. So what is the relevance of white matter microstructure and biophysical models in a tractometry course, you may ask? As you will see in the coming lectures, connectivity strength, for example, is a measure that is difficult to achieve using tractography. Why? Because the streamlines are nothing but a virtual construct that have no biophysical reality. And it's been shown by several studies that the number or count of streamlines cannot be a good indicator of connectivity strength across the brain. So people have suggested using other properties along the bundle to characterize this connectivity strength. Traditionally, perhaps fractional anisotropy, but more recently also white matter microstructure features such as axon density that can be integrated along the bundle and therefore give some measure of connectivity strength. But most importantly, these microstructure metrics can be used to perform so-called microstructure-informed tractography. This means that you can regularize your tractogram using this microstructure information. And for this, you have either bottom-up or top-down approaches that I won't detail in this lecture, but will likely be covered in the rest of the course. So in summary, very briefly, diffusion of water molecules in white matter is not free. It's affected by the axonal structures in the form of restriction and hindrance, and it therefore provides information about the tissue microstructure below the MR image spatial resolution. In the Gaussian approximation regime, meaning low B values, I can approximate my signal as a linear function, the log of the signal as a linear function in B, with the slope being the ADC, which depends on direction when the tissue is anisotropic, which is the case for white matter. And in this case, it can be fully characterized by a diffusion tensor with 3 eigenvectors and 3 eigenvalues. Beyond DTI, we can introduce biophysical tissue models, which in theory provide specific metrics of microstructure, but in practice, the output is highly dependent on the validity of the model assumptions and the fitting procedures, so do always inspect it with caution. But I'm happy to also say that there's been substantial progress in white matter modeling, both on the front of improved axon diameter estimation and the estimation of the main standard model parameters that we can now perform comprehensively. And these are now becoming accessible to applications and translation to preclinical and clinical studies of disease. Finally, all of these microstructure features are highly relevant for cleaning up or making more sense of tractography information, as you will see in the rest of the course. And I've included some reviews on white matter modeling if you wish to read more about these research. Thank you for listening.